The first case that we'll look at is example K, and what we're going to consider here is 4 cards. A player pays $4 and gets 2 cards, and the winnings are the sum of the um, numbers indicated on the cards, but what we want to keep track of is the net winnings, that is, the sum of the 2 cards minus the $4 payment. So first we need some way of visualizing this problem, and I think an event tree would be overly complicated in this case, so I suggest that we consider just writing down each of the possibilities, and we'll start with, whoops, we'll start with just trying to write down the complete set of possibilities. So first we could get a 1, first card's a 1, the second one's a 2, the next one's a 1, the second card is a 3, the first card is a 1, the second card is a 6. Next we could have a 2 and the second card is a 1, the first card is a 2, the second card is a 3, the first card is a 2, the second card is a 6. Then we could have the first card is a 3, the second card is a 1, first card is a 3, the second card is a 2, first card is a 3, second card is a 6. Then we have first card is a 6, the next card is a 1, then we have 6 and 2, and finally 6 and 3. And those are all the possibilities. What is the net winnings? What net winnings for each of these? The first case we have 1 plus 2 is 3 minus the $4 we pay, and so the net winnings is minus 1. 1 plus 3 minus 4 is 0. 1 plus 6 is 7, minus 4 is 3. 2 plus 1 is 3, minus 4 is minus 1. 2 plus 3 is 5, minus 4 equals 1. 2 plus 6 is 7, minus 4 is 3. 3 plus 1 is 4, minus 4 is 0. Then 3 plus 2 is 5, minus 4 is 1. 3 plus 6 is 9, minus 4 is 5. 6 plus 1 is 7, minus 4 is 3. Then we have 6 plus 1 is 7, minus 4 is 3. And lastly, we have 6 plus 3 is 9, minus 4 is 5. That was supposed to be a 3. I see also that I made some mistakes here. I got the 1 and the 6 right, but this one, that's supposed to be a 6 and a 2 there. I'm going to fix those. So that was supposed to be a 6 and a 2. That gives me 8 minus 4 is 4. And that's not my only mistake. Back up here, I did the same thing. 2 plus 6 is 8, minus 4 is 4. Now that I have it fixed, we see those are all the possibilities. So the possible winnings are minus 1, 0, 1. 2 is not possible. Then 3, 4, and 5. There are these 12 different possibilities that we've listed on the left here, and each of those is equally likely. So we have 2 occurrences out of 12 that would lead to minus 1. So 2/12 is got a probability of 1/6 for minus 1. We have 2 possibilities that lead to a 0, so we have a probability of 1/6 for 0. We have a positive 1 there, and we have a positive 1 there, so we have a probability of 1/6 associated with that one. Again, 2 is not a possibility, but we have 3 two cases that can produce a 3, so that has a 1/6 probability. We have two cases that can lead to a 4, so that has a 1/6 probability. And we have two cases that can lead to a net winnings of 5, so that's a 1/6 probability. And that's our probability mass function, actually. And if we wanted to calculate the CDF, all we have to do is keep adding these. So we'd start out with 1/6, then 2/6, then 3/6, then 4/6, then 5/6, then 6/6 as we move from one lump to another. But I should note that we actually would be able to have a value of, for x equals 2, capital F of x is equal to what it was at 1. So it's equal to 1/2. So it hasn't gone down at all there. So let's take a look at what that looks like. We have the PMF shown on the left, where we have the 1/6 probability associated with the net winnings of -1, 0, and 1, and another 1/6 probability at 3, 4, and 5, nothing at 2. But when we calculated this cumulative distribution, the CDF, we had to add those up from left to right, and we didn't have anything more to add at 2, but neither did we lose any value there either. So the capital F of x stayed the same at both 1 and 2. So that's the CDF and the PMF. And I didn't ask this in this case, but let's go ahead and calculate what the mean value for the net winnings is in this case. And we'll talk about that in a couple different ways that one could calculate it. The equation is that we just take the lump of probability minus the value that of x associated with it. So we would take -1/6 times 1/6, and then we add the next combination, so that would be 0 times 1/6 plus 1 times 1/6. So far, if you sum all those three together, you got 0. So we've had no net contribution yet because all those three sum to 0. But then we get 3 times 1/6, and we get 4 times 1/6, and finally we get 5 times 1/6. When we sum those together, we get 3 plus 4 plus 5 times 1/6, or 12 times 1/6, which is equal to 2. And it suggests that that is the mean value of x in our case. Does that make sense? Actually, it does. You may recall that when introducing the mean, I mentioned that if we have a symmetric distribution, the point of symmetry is the mean. And if you look at this, it's symmetric about the value net winnings equals 2. So we shouldn't be surprised that our mean value came out to be 2. Notice that that's not even a possibility. You can't get a net winnings of 2, yet that is the mean value, or the expected value of the this distribution. So is it worth playing the game? Well, on average, you can expect to win $2 with a typical draw. So not a bad game, but you're not going to become a high roller very quickly. That's it for case K.